Guten Morgen. Mein Name ist Darren Briskman und mein Deutsch ist schwank. That means good, right? So therefore, I will be doing the rest of this in English. So thank you for joining us on our database track. Oh, I almost got applause. Wow. See if I can earn some later. I have the easiest job at Amazon Web Services because I am the chief evangelist for database analytics and machine learning, which means my job is to make you excited about data. This is not hard, because if you're here, you're excited about data, right? Okay, let's set something. Every so often today, I'm going to ask you a yes or no question. For yes, do this. For no, do this. Okay, let's set something. There we go. So let's try that again. Is everybody here excited about data? Yeah, okay. About 3/4 you did this, and about 1/4 of you did this. I'm not sure what that means, but we'll figure it out later. I live in Oregon, so in Oregon that means that you're using certain herbs that I don't think are legal in Germany for personal use. But not my problem. All right. So before we go into the formal presentation, I was just going to talk a little bit about the things that we do with databases and analytics at AWS. Because we divide all this up into a couple of large categories. So one category over here is the relational databases. We'll talk more about each of these later. But the whole idea there is to have managed services. And we've discovered that managed services are the key to doing a lot of interesting things, like being able to operate at large scale and being able to do microservices. Now, if you're old like I am, you remember not that long ago, maybe 10 years ago, all the database questions were done. Everything was relational, right? The only question was, should you use Oracle or DB2 or Microsoft? But we're now in a world where we're seeing a whole revolution of non-relational things coming up. So we'll talk a little bit later today about what we're doing with things like DynamoDB, Elasticache, and Neptune, as well as other things going on in this non-relational revolution. And then, of course, we have the world over here of analytics. So the many things that we can do to understand data and see what's happening with the data. Now, the challenging thing, let's see if I can do this in the light, is to keep all of these different databases analytics working together so that we have some way to get some answers. Okay, that's as much juggling as I'm going to do. The other thing to be aware of is that today we are being live broadcast on Twitch. So I'm going to ask you to feel free to ask any questions. But normally I just ask you to shout them out. Because we're being broadcast today, I need you to raise your hand so we can get you a microphone. So here you're looking at a picture of me talking to you while I'm talking to you on the picture on Twitch. This also means that if there's anything you'd like to hear again, or any of the other tracks, you can listen to them at your leisure by looking at the Twitch broadcast. It's a little bit behind, isn't it? Okay. Can I mute the Twitch broadcast? I'll just kill it. There we go. All right. So the other thing to remember is that if you do ask a question, it will be on the internet forever. So make sure it's a good question. Okay. So we're going to start today by talking about microservices. And one of the things I find amusing is that I gave these nice short titles to our German team, and they made all the titles longer. So this went from microservices to a slightly longer title about data design and modeling for microservices. But we're going to talk a bit about microservices and how that fits in. So I'm going to ask just a few questions. How many people here consider yourself developers? Okay, that's good, because this is Dev Day, so this is what you should be here. Some of you did not raise your hand. Is anyone here, you think of yourself mostly as a data professional, a database administrator, a data engineer, or a data scientist, or something like that? Okay, nobody. All right, so yes, sorta. All right, a little bit. Anybody here think of yourself as an architect? A few of those. I don't really know what architect means. I spent 14 years of my career at IBM, and I was involved in a 2-year-long project there to define architect. And the only answer we came up with is, we think you're smart and we don't want you to manage anybody. So I hope that fits the architects here. My own definition of an architect is someone who can answer any question with, it depends. So that comes up to, I was an architect. So what does it depend on? Well, partly it depends on how you're going to put your services together. And microservices are one of the big buzzwords that's been around for, 10 years or so. And it comes from a very simple need, which is the need to work at internet scale. That the whole reason that drove microservices was we're moving from a world where an enterprise application meant a big SAP installation with a few hundred users to an internet application with millions of users. And microservices are the only way that's yet been shown that you can build large applications at scale to this very large size, as well as being able to do things quicker and more effectively, developing new features that meet the needs of your organization. So my last hand-raising question for now, how many people here are currently working on some sort of microservices project? Okay, well good, then you're in the right session. For the rest of you, try to stay awake. So, at Amazon, we started in a traditional way. 1995, when the first Amazon.com was built, it was a monolithic application built with Oracle and Memcache. It took us about 4 months to realize we couldn't afford to use Oracle the way that we hoped to grow. So we went to this 1.0 version of a brand new database called MySQL. And MySQL actually came out 21 years ago is when I first started. So we built the business on MySQL and Memcache, went really well, launched to the public in 1996. 1997, Amazon was the first company to sell $1 million online. 1990, it was the first company to sell $1 billion online. An American billion, that's still a lot of money. So very quickly we were growing, but that was 2000, it was $1 billion. Very quickly into the early 2000s, it became clear that we were not able to keep up with what we needed with a monolithic application. And we started splitting this into small independent services. Today, if you go to Amazon.de or Amazon.com, you're looking at about 210 to 230 microservices that are coming into play. So I asked the architects over at Amazon, could you give me a map of what all of our microservices look like? And they said, it depends. I told you, they're architects. And I said, well, what does it depend on? It says, it depends if you care if anybody can read it. He said, well, just give me the map anyway. And they said, okay, but nobody will be able to make any sense out of it. And they were right. However, everyone who registered for this, next week you will get links to all of the slides and all of the tracks. And if you zoom in on this, you can see that each of those little blocks is indeed a well-defined microservice, or at least a named microservice, and a list of how they connect to each other. So when we first started this, it went down the path of it being service-oriented architecture with each service being a single purpose. But I'm going to share with you some of the things that we've learned about making it work. One critical one is they connect only through APIs, no backdoors. So the only way to talk to each microservice is through its API. The only way for microservices to connect to other things is through an API. And that they connect. Now, initially, we did it all over HTTP, HTTPS. Sometimes today we use MQTT or other pieces, but it's all standard network connections. And this is not easy. Distributed computing is hard. This is more difficult to write than traditional computing. It's just more work. You have to have multiple databases across multiple services. You have to find ways that you can live with eventual consistency, which is very disturbing to a lot of developers who've never dealt with this before. That the idea that I can ask the same question twice in a row and get different answers, because I'm not always going to have all my data consistent. Consistency is very expensive in a microservice environment, so you only use it where it's really necessary. Lots of moving parts. You have to have ways to discover services and coordinate them and route them. Ultimately, it's a few things you need. Every microservice has to have some sort of registration. There has to be some sort of repository that explains what the services are. There has to be some method of discovery. Services have to have a way to find what other services are available and where they are. You can't have them hard-coded IP addresses. That will fail. That's part of the wiring, the way that these services connect. And you have to think about how you administer them. You also have to deal with state. A microservice must be stateless, or it's not a microservice. But you're going to be storing some state, so that state has to be in some sort of data engine. Now, that could be a flat file, that could be a high-speed database, that could be an in-memory structure, but I have some sort of state management. And I need to have metadata, and I've got to have versioning. I think the number one mistake I see when people first start using microservices is they fail to think about versioning. But you build your first microservice, then you build your second, and then you build your 10th. And by the time you've got 10 microservices, you've probably got a matrix of about 50 services and versions going on. So how do you deal with that and use that effectively? And then you need to deal with caching. It's almost always going to be necessary to have at least some of the microservices have some caching layer in order to accelerate the performance. Because each microservice is going to be fast. And each microservice is going to be able to talk to other microservices in only a few milliseconds. But if I've got 200 microservices talking to each other and they each take 50 milliseconds, that adds up to a long time. So I'm going to be needing to use caching so I can get to sub-millisecond times. And then we have to find ways to make it low friction to deploy and automate the management and monitoring. This is all a lot of work. So what does it actually mean when we do this? Well, here's some of the other things we found. One, make sure that you are not committed to any technology stack. Now, when you write a microservice, when you put one together, it's got to be flexible. Today at Amazon, when we write things, our usual database choice is DynamoDB. Is that what we're going to want? 10 years ago, that our choice was MySQL. Will our choice be 10 years from now? I don't know. But it depends. Thank you. That's the correct answer. And it depends on what happens in technologies. But we need to make sure that we're not stuck with a stack, not trapped with any language, not trapped with any technology, because these need to be able to change over time. You end up with this polyglot ecosystem. It was common belief in IT that the most important thing you could do was centralize and standardize and get everybody using the same tools. We're now 180 degrees away from that. Probably more accurate to say we're 540 degrees away from that, because as an industry, we kind of all turned around in a circle and ended up pointing the other way. So we have to find a way, we have to live with the fact that I'm going to have different tools, different databases, different languages, all living and working together. And polyglot persistence, not one big database. Lots and lots and lots of little databases. Generally, one database per microservice pattern. Now, that might not mean a physical database instance, right? It could be a DynamoDB table per pattern, for example. But I'm still going to have many, many different databases and data stored in many places. This is necessary for scalability. It also leads to a problem, because what's going to happen whenever you have the same data in two different places over time? They're going to, entropy, right? They're going to go out of sync. So part of what we have to do is write some extra microservices every so often that go make sure those databases get resynchronized. This is, again, a lot of work, but it's necessary. Because now we start talking about what we get from doing all of this work, and there's some big benefits. One of them is being able to do low-friction deployment. And the two key methods of this are canary and blue-green. So if you've never heard of these, canary comes from coal miners who would take a canary down in the coal mine. There's a good reason for this. Canaries are very susceptible to poison. Also, there's no music in the coal mine. They didn't have, iPods back then. So if the canary stops singing, run. In microservice, I'm sorry to keep coughing in your ear. In microservice, the canary deployment means you have most of the users using the old version and a few users using the new version. And then you see how that works. And if that works well, you do a few more in the new version. And if that works well, you roll everyone to the new version. So for example, within the Amazon.com world, we recently rolled out a new search engine. Now, most people wouldn't see this. You just see the search bar. But initially, we set it up so about 5% of users would get the new engine, 95 would get the old. Worked pretty well. Next day, we changed it to 10%. Found a few bugs, rolled it back out. Went back to 5, it worked. Went back to 10, it worked. Went up to 25, it worked. And then everybody had it. So this gives a low friction deployment, non-disruptive. Sometimes you can't do that. For example, when you're rolling out a new database, you probably can't have some people on an old one and some on a new one, or a new database version. So in that case, you do blue-green. So I have my blue version that's running, and I have my green version that's a new version. And when I'm ready, I can just change the DNS address and flip it over, and now everyone's over here. I'm probably going to be synchronizing data. And then once I flip over, I synchronize data back the other way so that I can flip back if I have a problem. So I flip that over, run it, and then if everything's great, great. If not, flip back, and then do that as necessary. If you do this right, you can do it with an outage that's less than a second. So it's not really disruptive to users. So at Amazon and most places, that's called blue-green. At Netflix, they call that red-black. I was always curious about that, and then I spoke to the head architect at Netflix, and they said, why do you call it red-black? He said, because the first architect at Netflix was blue-green colorblind. So, okay, that's a good reason. So these are low-friction deployments. All right, so if you're doing this right, let me give you some of the lessons that we had to learn the hard way over 10 years of building this out. 1, each service must be elastic. That means a service can grow or shrink independent of the other services. This is absolutely critical to scalability. So I'll give a good example of this. Anybody buy anything during Prime Day last year? Amazon? A few nods. So on a normal Tuesday in the summer, the DynamoDB that's sitting behind Amazon.com does 3-4 billion queries a day. On Prime Day, it did about 90 billion. On the other hand, the system that tracks registered users, I mean, you got a few new users, but it only went up a few percent over a regular day. So we want to make sure that the things that have the higher use can go up and down, independent of other pieces. That's critical to microservice. Second key piece is that it's resilient. You have fault isolation boundaries. You design so that when a service fails, not if, when, all software will fail eventually. So when a service fails, limit the blast radius, limit how many other things it affects, and make sure we think about ways to recover. Make it composable with APIs, and the last two are really hard. Make it both minimal and complete. Minimal means keep the service as simple as you can. Complete is make sure the service does everything the service needs to do. Those two are friction with each other. They compete. But the last thing here is perhaps the most important thing and the biggest mistake I see made. Loose coupling is critical. Tight coupling is when one service directly calls another service. When one service calls another service, they're not really two services anymore. You've just made them a single service. Because if I change anything in one service, I have to test it across them both. And that means any changes become large regressions, and I've really just made another monolithic application that I'm calling microservices. To make microservices work, they must be loosely coupled. Loosely coupled means services never talk to other services. Services write data into queues, and then other services pull data from the queues. Now let me be clear, a queue here does not mean IBM MQ. It could, or Amazon MQ, or RabbitMQ. Or it could be a file that one reads and another writes. Or it could be a database entry. Or it could be a Redis entry. It's some place that that data is. The point is they're loosely coupled. Now, services write into queues. And now I could have the target service, the B service in this case, read the queue. Or I could have the queue itself push something out. Or I could have things happen on a schedule. There's many ways that this could work. But the key point is that I use loose coupling, that every microservice reads and writes only from some sort of queue. This allows separation. This allows elasticity. This means that the development team that's working on A never needs to really talk to the team that's working on B. They just need to know what the APIs are. and they can develop and work independently. And those are the reason you do this stuff. Because I get faster development when I do this. I get more rapid development. I get the ability to do things much faster. At Amazon, before we started down the path of microservices, we had a quarterly release train, and once every 3 months we could put new things onto the website. Today, across all of Amazon globally, we have one new release of some significant feature approximately every 1,500 milliseconds. So every 1.5 seconds, someplace on some Amazon service, something new is being developed and deployed. We're able to do that with low friction because it's all microservices. It also lets you do parallel development. So there's an old bad joke in computer science that 9 women cannot make a baby in 1 month. But they can make a microservice in 1 month because they can each be working on different parts in parallel. They don't have to do it together. So babies are monolithic. Don't try to change that, please. But microservices are not. They allow us to get parallelism to work. You've all seen this. Have you ever seen that, or have you ever seen this, that you're on a team and the team is behind schedule and your managers go, no problem, we'll put extra developers on the team. Does that make it faster? No. In the long term, it might. But in the short term, now everybody who is developing is now helping the new people understand what they're doing. But if I can isolate these things into separate microservices, then what I can do is say, split those functions out and say, okay, this team work on the display engine and this team work on the search engine. And we're able to do those things in parallel. This is why it's worth doing all this hard work, because I can do things fast and parallel, and I can do true DevOps, or as we now call it, DevSecOps, right? All right, another hand question. How many people here today believe you work in a DevOps environment? Okay, is it true DevOps? Do you own it? Do you build it? Do you deploy it? Do you secure it? Do you own the roadmap? Do you control the tools? Because that's what real DevOps means. It means that team has complete authority and accountability for what happens. But there's also, doing all this work means I get more scalability. I can build things like Scout 24 and Amazon and Airbnb and these other really giant applications and Google and other things that have hundreds of millions or billions of concurrent users. I get higher availability, I get better fault tolerance, and the official line is more closely aligned to the business domain, which is a business speak way of saying that when the business people want something, they can actually get it in a few weeks, not in a few years, the way it traditionally has worked. Now at Amazon, we do this with something called the two-pizza team. Each service, each microservice is owned by a small team. A team that when they stay late, 2 pizzas is enough to feed everybody. Now, when I started at Amazon, my wife heard about this and said, good news, Darren, you're a 2-pizza team all by yourself. Yeah, well, that's more of a personal flaw than a design characteristic. But I would point out that in many of our 2-pizza teams, there are fierce arguments about what kind of pizzas to get. But we do occasionally do that. But the point is, how many people is a 2-pizza team? Somewhere between 6 and 10, usually. And that team has complete ownership. That means that team picks what we do. We call them service teams. They own the primitives. The service team is responsible for what the service does, for publishing the APIs, for determining the roadmap for the service, for supporting the service when calls come in, when there's a problem that it doesn't work. You own it, you run it, you build it. It's up to the service team to determine what tools they use. So our default choices at Amazon, for example, are Java and DynamoDB. Or if it's customer-facing Node.js. But if your team says, you know, I'm doing something that needs a lot of geographic information, I'd rather use Postgres, you can use Postgres. It'll be a little more work for you to support it because you won't have all the support tools, but that's up to you. That's your choice. And if you want to go way out and say, no, we have to write our own database for this because our needs are so weird, okay, good luck with that. But if that's what you choose to do, that's what you choose to do. And each team has complete choice as to what tools they're going to use and how they're going to deploy them. The only places that we force things down have to do with security, and network connectivity and other things that have to be universal. So each team has complete ownership of this. Not all of the teams are writing services that a customer would see. Some are writing services for other service teams. So we have thousands and thousands of service teams at Amazon. And as mentioned here, organizationally, they roll up to various units. So the biggest two units at Amazon are web services and commerce. And then there's many smaller units. A good example of a small unit is Twitch, the people who are broadcasting us right now. But Twitch also is a collection of service teams. We have some very small services that are just one team. We have big ones like commerce or web services that are thousands of teams. But this lets us build a way that enables us to do things quicker and effectively. So, since this is the database track, now that we've talked about microservices, how does the data work underneath that? And what's the data architecture? Well, again, the traditional way to do this was a monolithic data store and put all the data in one place, all together, one big database doing all of your services. This was the best way to do things 10, 15 years ago for a very simple reason. Database licenses are really expensive. And a lot of choices were made to minimize the database license expense rather than go for what's best for the business or what's best for innovation. We believe that this is an anti-pattern. That when you're in one big database, it's too hard to change, it's too hard to advance, and your costs are high. So what we end up with in the microservice world is polyglot persistence, decentralized databases. Break the big database into many smaller databases, some of which will be redundant with each other. Each service chooses its own data store technology. So in this case, I might have one service that chooses Dynamo, while another service wants to run on MySQL, which in the Amazon world would be Relational Database Service, or RDS. And yet another service, the one on top, says, well, I need high-speed caching, but I also need persistence, so I'll choose Elasticache, which is Redis, and also RDS. Each team makes that decision. Data is gated through the service API, and they're independently scalable. Which leads to some challenges at the data layer. Like, how do I do transactional integrity? When I do polyglot persistence, I'm always going to have eventual consistency. So generally, I'm going to do asynchronous calls, which are non-blocking, but I have to handle them. So I'm going to do things like stage commit and rollback on failure, and the way that you do that is through what's called a correlation ID. So as data passes from one service to another service to another service, you make sure that you have some sort of ID that identifies this transaction. So again, I'm using an e-commerce example, but I'm going to have a UI and a catalog and a checkout that goes to payment and shipping. I'm going to make sure that as those go along, for a given transaction, there's always going to be a common UID. In this case, UID 123. And I need that because if I have a failure, I want to be able to roll back everything on UID 123. That could happen for two reasons. It's called business failure or technical failure. The best practice for this is to have a rollback microservice. So you have another microservice whose whole job it is to roll back when things don't work right. So what do I mean by the two different types of failure? Well, a little more on this later, but a technical failure is when something doesn't work. A Lambda function failed. A database crashed. It doesn't happen much in managed services, but it can still happen. A business failure is when the technology works, but there's something wrong with the data. So in the case here of e-commerce, what happens if I get all the way to the end and the credit card is declined? All right, well then I have to roll back that transaction. Go back to the user and say, there's a problem with your credit card. So we're going to do this have functions in the microservices, and some of those functions are going to be a rollback function, and then optionally a commit function, so that these aren't actually committed until the commit function is called. And these are APIs you build in your microservice. Now, one of the ways to make that easy is DynamoDB, and this is why we normally use DynamoDB at Amazon for our own services. Because whenever you change data in DynamoDB, it's exposed as a stream. And the streams are ordered and persistent for 24 hours so that the data stays around as accessible. And the stream can itself drive Lambda functions or drive other things to happen. So therefore, you can attach yourself to the data of interest, and it'll keep retrying until whatever you want to do actually happens. But when I get those errors, I have to have some way to do rollback. So what we usually do is we create a transaction manager microservice that can tell all the other microservices time to roll something back. So often, DynamoDB will be the trigger that makes that run, but there'll be some sort of correlation ID. So what we'll do is when we have a failure, we'll have an error table in DynamoDB. And into that error table, you will write the UID of the correlation ID. That will create a stream. The stream will then kick off the various functions that say, go roll all this back. Make sense? I know this sounds a little bit complicated, but it's a lot easier than it sounds. So then we end up with something like this, where I'm rolling along and I run into an error. Then that error writes to the error table. If you like, you could also put it into an error stream or an error queue, and then that'll kick off my transaction manager function, which will then go and do rollbacks against each of the places I had a problem. Now, what if I have bad code or a physical failure? So I'll put it this way. Lambdas are serverless, right? I'm assuming everyone here knows what a lambda is. Is that correct? Okay. All right, once again, 3/4 are doing this, and 1/4 are kind of... Is my English that bad? Okay. So when I'm running lambdas, a lambda actually runs in a container. Right? Now, it's serverless means you don't have to care about the server, but it's not magic. It tells to run on a server someplace. Do containers fail sometimes? Yeah. I mean, right now, the service level agreement for EC2 is 99.95, and we're actually running about 99.98. But even 99.98, that means that about 1 out of 200 are going to, or 1 out of 400 are going to fail each year. So once in a while, I have a failure. Now, in Amazon, that'll automatically get fixed and replaced, but it means something failed and might need to get rolled back and restarted. You find this in AWS on CloudWatch logs. So whenever I have any sort of physical failure or code failure, that'll show up in CloudWatch. So I need to make sure I set up some metric filters to have CloudWatch also be able to have the alarms kick off my transaction manager so I can roll things back. Now, a little warning about this if I'm using the stream. Another mistake I commonly see. Make sure when you write your lambdas that pick things off the stream that they acknowledge that they got it off the stream. Because remember, the stream keeps pushing it until it's picked up. So I've seen code written that it says, "Oop, there's a problem, I'll do something," but it never acknowledges it. So what happens in the stream, the head of the stream is still that same problem. And any future problems are backed up behind it. So you got to take it out of the stream when you're done so the next problem can come to the head. So just a little piece of deciding that. So in any case, we'll watch the CloudWatch metric and also look for, in this case, look for a metric that if I see the same correlation ID keep coming up, means something's not acknowledging the stream. Okay, last trick in here, keeping the data consistent. This is master data management. So you'll probably need to write yet another microservice whose whole job it is to look across your different data stores and make sure the data is consistent. So make sure that the data coming in and the data coming out actually match. Make sure that when I have data in different stores, they're kept in consistent ways. Make sure that if you're doing equity trading, that all of the systems that are trading equities use it the same way, so that I don't have this one says Apple and this one says AAPL, but that I have those things regularized. And that's what we do with the master data management. So it's yet another microservice you write to watch other services. Usually this is something you want to run on a schedule. So the trick, of course, to running the functions on a schedule is set up a CloudWatch event and have the event just kick off once an hour or once every 10 minutes or however often you want to check it. All right, so what database do I use under all of this? Well, the good news is, AWS, we have lots of managed databases. The bad news is, we have lots of managed databases. And the truth is, almost anything you want to do, you can probably do with any of these. Right? I could use a relational database. I can use Elasticache if I want something really fast, which is Redis. I can use DynamoDB if I want something really scalable. I can use RDS if I want something that uses relational technologies. Redshift I don't normally use in microservices except for analytics, because Redshift is a data warehouse. It reads very fast, but it writes a little bit slow. So it's usually not in the right time scale for this. But I might want to store things on S3, or I might want to store them in Elasticsearch. Some people actually use Elasticsearch not just as a search engine, but as the queue to move data back and forth. Or stream it in Kinesis, or some combination of these. Now notice what I have on the side there doesn't say microservices service, because the service is a whole bunch of microservices that does something. Again, to use the Amazon example, the Amazon homepage is a service made up of a few hundred microservices. So, how do I decide which service to use? Usually we say if there's a functional reason that overrides. So one example of a functional reason is I need to be under a millisecond. Okay, if I need things to happen under a millisecond, I pretty much have to use Redis, the in-memory data store that lets me do things in microseconds. Another functional example is one I mentioned earlier, which is geographic information. Because Postgres is the only database today, arguably Oracle, that really have strong GIS capabilities, Great Geographical Information System. So that if, for example, I want at the database layer to draw a bounding box and determine if a given lat long is in that box. And usually a box doesn't mean a square, it means like the borders of Bavaria. Okay? Bavaria is not a square, right? It's a very complex shape with all the things around the border. Postgres does that really well. But if you don't have that kind of very specific functional need, then we recommend you do this off of non-functionals. So what you end up doing is you create a chart like this one specific to your organization. And you might make, in this case, 4 different categories. And you determine for your organization what those categories are. So for this organization, they've decided that high latency, things that don't need a big latency can take more than a second. And their idea of very low latency is less than 20 milliseconds. Now, for your organization, low latency might be 1 millisecond. Depends on what you're doing. Similarly, we define some levels of durability, some levels of what we think are big or small on scaling, some levels of how available they need to be, how public the data is, how quickly they need to be able to recover. So the highest level is data that I have to recover in 5 minutes if I have an outage. And then what level of skills they have in the organization. You use this to then determine what's the right database for me when each service team is figuring out what to do. So the numbers on this chart are not service level agreements. They're rough numbers for what we see off different services. But for example, with latency, my relational databases will usually be under 10 milliseconds and always under 100. But when I'm using Elasticache or DAX with Dynamo, I can get that down to 1 millisecond. S3, on the other hand, has infinite size. Okay, not really infinite, but really, really big. We have some customers that have moved. One well-known customer is Snapchat. When they joined AWS, they moved over 4 exabytes of data into AWS, into S3. So we have really big size on S3. On the other hand, usually you don't need that much. Usually you don't need exabytes for your data. If you do, you might be keeping a little too much data for that microservice. So other things have their own limits. And then most of our services are highly available, some more so than others. Various recoverability. If you're not familiar with MAZ, that stands for multiple availability zone. That's just saying, have I checked off the box to have this spread across high availability or not? Some services, like Dynamo, you can't turn that off. Other services, you have a choice. And then you finalize your choices that you've made. So you look across these and say, after I have mapped these together, I end up with a short list. And then I decide which ones I want to use. So that gives me a choice for which data store to use for which project. Often I will use multiples in a project. So let me walk through this in a real example. I'm currently working with one of our customers that does settlement of bond trades. So usually this is government and government bond trading, or government to banks. So the problem here is the average transaction is $50 million per transaction. And if the transaction gets delayed, the settlement company has to pay the interest on the delay time. Now you might say, well, it's only a few hours. But when we're talking about hundreds of millions of dollars, that adds up very quickly. So they settle a total of about $3 trillion per day of total bond sales on a typical working day. So $3 teradollars. It's a lot of money. So what are their requirements? So one requirement they have is that when things are ingested in from the banks, I have to ingest that and absolutely reliably do it within 30 seconds every time. And then I need to pass that through various services that are going to process it. And then at the end of the process, I need to write that into something that is persistent and long-lasting and can be accessed by SQL because there's some standard queries that people in the industry write. All right, that gives me some definitions, right? So my one coming in where my size is very variable and I've got to always be within 30 seconds, what do you think is the right choice there? What would you use? Say that louder. Even louder, because my ears are stuffed. Okay, this is a tough room. All right. Dynamo is what they ended up choosing. Because we could have done that with Dynamo, we could have done that with relational. But one of the features of Dynamo, as we'll talk about later today, is Dynamo you get the same performance no matter how busy it is. And they wanted to make sure, because when you're in bond trading, most days you have a certain amount of busy, but some days something happens and you're much, much busier. So they want to make sure they always hit that 30-second mark. The other trick that they do is they're writing it into 2 different regions. So they're writing in the 2 places in the world, just in case some disaster happens, they don't lose any transactions. However, so that's my highly reliable Dynamo for ingestion. Through the process, they'll have lots of little Dynamo state engines just holding data, or sometimes Redis as queues to move data from one service to the next. And at the end, I need something that's highly reliable and I can answer a query in SQL. So Dynamo doesn't support SQL. So what would you use there? Aurora, right? In their case, they looked at MySQL and Postgres. They decided they liked Postgres better. That was a skills issue. Because before they used the cloud, they were mostly Oracle. Postgres is much closer to Oracle, just to the syntax and the way it operates. But that's the way we kind of walk through these non-functional requirements in order to determine the data stores to use. And of course, with Aurora, they're also writing it in the 2 regions, just so we have 2 copies. And if I have some sort of disaster, I don't lose my data. So you finalize out that choice. And usually, in most organizations, you don't force the service teams what to use. But you might have a service team whose job it is to help the other service teams by putting together services to make it easy to deploy something. So within Amazon, we have teams that make it easy for people to use Dynamo. We have teams that make it easy for people to use Aurora. We have teams that make it easy for people to use Elasticache and pre-configure them into our security standards and other pieces. Last piece you have here is how do I report on how things are working. So you have to do some sort of consolidation and aggregation. There's 4 patterns for this, and 3 of them are good. So the pattern you should never use is the one in the lower right, which is the composite, which is when I write one data service that tries to live read information from different services. It doesn't scale. Again, it's tightly coupled. I'm reading directly. So don't do that one. Each of the other 3 works. The most common one I see is the one on the top left, which is a pull model, so I will have the data get copied or pulled into the aggregate reporting service. The one that I usually prefer is the one on the upper right, which is a push model, which is a fancy way of saying have every service emit a log. So every time something important happens in a service, have it write a log. And then my reporting section is just log analytics. And I can use Elasticsearch or Elk Stack or Splunk or a whole bunch of tools that make it easy to analyze all the logs. The other one I've seen some people like to do, especially if it's widely distributed across different regions, is publish and subscribe, so that you have each of the services actually are a publisher that will subscribe, and then the data aggregation service is a subscriber. But all of these work in order to get the data in. Back to my description of the bond settlement system. Whenever I have an ingest, I emit a log. Whenever I write a final version, I emit a log. Every so often, we compare the logs. Because if something went in and it didn't get to the other end within a minute or two, something funny is going on. I need to go back and find out what happened to that transaction. This is, again, one of our ways to avoid entropy. There will always be entropy. Don't pretend it doesn't exist. Find ways to deal with it. So, final thoughts. Use non-functional requirements to identify the data stores for each service. Use polyglot persistence so that I don't have bottlenecks, that each of these things are able to scale and move independently. Embrace eventual consistency. Learn to love it. Think about which things you're doing that don't need to be perfectly consistent. When you're saying, how much inventory do I have? Does that need to be an exact number? Usually not. When I'm saying, what's the temperature outside? Does it need to be accurate within milliseconds? Yeah, if it's 10 minutes out of date, it's probably close enough. Other things need to be exactly accurate. Understand which ones need them and only do that work when it's there. And then think about your analytics requirements in the beginning. So if you put all of these kind of tools together, use some of these things, you too can develop microservices. They'll let you create applications that are flexible, scalable, changeable, let you deal with the new world. So does anybody have any questions? Oh my God. Am I that boring that nobody can come up with even one question? Or are you so frightened by the warning? Oh, there we go. All right, Grant, you get to run over with the microphone. And don't let the fact that you're live on the internet scare you in any way.
This is basically on the blue-green deployment, how it is done. Do you really duplicate the whole infrastructure, or is it only at a service level you duplicate the services and the databases are, underlying databases are the same? Because it amounts to the cost at the end.
So normally when I want to do blue-green, I only want to do one service at a time, right? I don't want to do the entire environment unless I actually have a change that affects the entire environment. So usually my blue-green switch is I'm blue-greening, switching out one specific service with that switch. On the other hand, if I really need to do multiple services at once, this is what's great about the cloud, right? Because if I need extra capacity, I use that extra capacity, and when I don't need it anymore, I can turn it off. So I can do those things temporarily and do them. The other thing that I like about the cloud is the ability to do full performance testing, which is something I always recommend, is if you should be testing these microservices, have test copies of them, and test it against the full performance you think you'll need. Because that's the only way to discover whether a high workload is going to break your service or not. Well, no, I'm sorry. There's another way to discover it, which is not test it and find out in production. I don't recommend that method. All right. Any other questions? Yes, sir. Well, let's let them get you the microphone here. Come on, Grant, step it up. All right.
I have a question regarding loosely and tightly coupled services. You
Okay.
mentioned the service discovery. If I have a microservice and I'm using some kind of service discovery from like Console or Eureka from Netflix, is it tightly or loosely? Because I'm not using any IP address, I just know the name of the service, but still I'm using the REST interface from the service where I need the data from.
Okay, so in that case, if I look at how Eureka works, what I'm actually doing is moving the service information through an API call into the service registry. That is a loose coupling, because the service registry isn't really calling, it's going through the API into a data store. So if you think about the way Eureka is defined, it really is a loose coupling environment. The point is the discovery service is not, well, sometimes in that case the discovery service will directly call in order to fill its data store, but in this case it can be eventually consistent, so it's not a tight coupling. And I will say don't let the computer science definitions become the enemy of making working services. Everything I just said, no tight coupling. I've been working in some environments where people say, I've got to get all this done in 50 milliseconds. All right, well, if I have a 50 millisecond budget, I can't do a lot of jumps. So in that world, sometimes you have to break the rules and actually do a tight coupling. Just understand what you're getting and what your costs are when you break these rules. Okay. Someone else had a question back here.
Yeah. It's actually a similar question. I'm just trying to grasp the concept. You said that you should loosely couple the microservices, but when you're calling the service, another service through the API, are you actually then pushing the response to the queues, and with this you actually decouple the services?
Yes.
Or is there other idea behind it?
So generally, when one service is calling another service's API, what you really want to be happening is that it's calling upon something that is queued and some data that is there. So that when I need one service to call to another service, if it's a push model, the queue itself should be kicking something off. So this is when I'm going to use streaming or some sort of Lambda function. If it's a pull model where this service is pulling from that other service, it can call the API from that service. That's okay, as long as what's behind that, what it's actually pulling from, is some sort of queue. So I want to make sure I have the queue exposed by an API, but that the pulling function does not require tight integration with the rest of the service. So as you probably have noticed, what I'm doing right now is a 1-hour version of what's really a 3-day course on designing microservices. So if you do that full version, whether it's from us or others, there's a lot of examples about how you can do this and make the microservices work. But again, what we're really trying to avoid is creating a world where change to one microservice requires regression testing against multiple microservices. We're trying to make the microservice isolate so that all I need to know about that microservice is its APIs, and everything else is black box to every other service. Okay.
The question is, as we saw from your images, that for microservices API you use mostly HTTPS, and I actually tried to Google in microservices HTTP versus messaging, and first question lands on Stack Overflow, which starts with word, I heard Amazon uses HTTP for its microservices. So what is the main reason? Is it only HTTP, or you mean it's mostly HTTP and in some cases messaging?
So if I'm doing, when you say messaging, what do you mean? Grant already took away your microphone. So if by messaging you mean a lighter weight protocol like MQTT, sometimes we will use that today. If by messaging you mean actually passing a message in the terms of like a message queue, well, that's passing over HTTP services usually. Now, within Amazon, we started enforcing the rule about 3 years ago of all HTTP had to be HTTPS, that everything should be secured. And indeed, I think in today's world, there's no reason to ever use clear text HTTP. That just opens up a security risk that there's no reason to open up. But beyond that, the main reason that we're stressing that is to make it clear that I'm using standard network topologies and that I'm not writing special networking pieces for my microservices. So for those not familiar with MQTT, that is a very lightweight design for Internet of Things. But sometimes it makes sense if I need to do high volumes and I have an application layer that will take care of consistency. Because it's essentially a high-speed to UDP equivalent of moving data. But there are times that it makes sense if I need to move data very lightweight. All right, one more question.
Hi, my question is regarding loose-coupled microservices. And as you said that every time a microservice has to write in a message queue, so if you got transactions which are very much time constrained, then every time publishing or subscribing to those message topics, won't it like increase the latencies?
So the short answer is yes. It will increase the latencies. So then how do I deal with that and do it? So one way is to use very low latency. If I care about latency deeply, use very low latency queues, usually an in-memory store like Redis. The other piece is loose coupling sets you free. It gives you parallelism. It lets you grow. But if I've got a hard business requirement that I got to get these 10 services done in 50 milliseconds, probably can't have them all queue in there. I'm going to have some faster ways. Having said that, In Redis, in Elasticache, as we call the hosted Redis in Amazon, I can read or write a 1K object in about 200 microseconds. So given that speed, I can usually do many hops and still be within my budget. Again, this is one of those functional requirements you have to care about. All right. If you have more questions, I'm going to be hanging out here, so come up and talk to me. Otherwise, I have 2 requests of you. One, go talk to our partners. These are the fine people who paid for the pretzels this morning, and the other stuff. And please, go out there and do something really cool with microservices. Thank you for your time.